Hi, my name is Dominic Mesiti, and this is my peer-created assignment for Coursera's Machine Learning Foundations for Product Managers course. In this project, I have the opportunity to apply my new knowledge of the modeling process to develop a machine learning model to solve a simple problem. A small dataset is given for this task, and to perform the basic steps of modeling process to train and evaluate a machine learning model on the dataset. The first step in this exercise is to determine the machine learning approach and the output metric on the given dataset. In this project, we will build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. First, we need to identify the possible features and algorithms of the information given. If we look at the features, we have a set of 9,568 hourly average readings from sensors at the power plant, which we will use in our model. The columns in the data consist of hourly average ambient variables like temperature, ambient pressure, relative humidity, exhaust vacuum, and then the net hourly electrical energy output, which is also the target that we're trying to predict. Given that we are predicting a continuous variable, which is the net PE, this is a regression problem. Suitable output metrics for evaluating the performance of regression models include the mean absolute error, the mean squared error, the root mean squared error, and the R squared. For this exercise, we will focus on mean squared error for the given information. If we look at information, I think that two different models can be compared, which are the linear regression model and the polynomial regression model. To do this exercise, I use the data analysis toolpack in Excel to do this regression analysis on all information given. First, we need to split the data set into a training and a test set. A common approach is to use a 80-20% split, where 80% of the data is used for training and 20% of the data is then used for testing. Afterwards, we need a validation strategy where we compare the different models. Therefore, we will use a fixed validation set, which means that we will be using the split training and test data set for validation. Before we do the analysis, here are a few scatter models which demonstrate the relationship between the variables, where on the left we are using all variables for the regression analysis, while on the right we have the polynomial model, where we use a polynomial formula which is typically a squared value of the information given. As you can see, a strong relationship and positive correlation is shown for both models. This is the first model, the linear regression model. A few numbers are important from this table, and this is a table taken from Excel. What you need to look at is the regression statistics, and it tells how well the calculated linear regression equation fits the data. As you can see, it's 0.928, which means it's 92.8% of the dependent data, which are the BE values, are explained by the independent variables, which are temperature, vacuum, relative humidity, and ambient pressure. What is also important in this table is a significant F. This value is low, which suggests that the differences in the means are unlikely to be attributable to chance fluctuations within the group. Typically, we're looking for values between 0.05. If that condition is met, we can also look at the p-values. These are all well below 0.05 to prove the statistical value of the different metrics being used. This slide represents the output of the prediction calculation. I produced this table by using the coefficients which are used to calculate the predicted PE for the variables. The formula used is I have the intercept, I add a product of the coefficient of the temperature and the temperature itself, the coefficient of the humidity with the humidity itself, the coefficient of relative humidity and the humidity itself, etc., etc. From the predicted PE, we can calculate the mean squared error, which equals to 20.78 for this model. If you look at the next model, which is the polynomial regression model, I do the same exercise, and if you look at this at the variables, you can see that they show a important validation of the model itself. Although you will see that from the adjusted R-square value, it's a bit lower. It's 87.5%, but the significance F values and the P values are well below the 0.05 to show statistical correlation. And then this slide represents the output of the prediction calculation. By using the coefficients, we can calculate the predicted PE for the variables. It's the same formula as in the previous model, but now we take the polynomial values instead of the original values. Then we use the predicted PE to calculate the mean squared error, which equals to 36.46 for this model. So if we compare the models, we see that the linear regression model shows a MSE of 20.78, while the polynomial model shows an MSE of 36.446. As lower MSE values prove a better fit, thus the linear regression model will be used on the testing data. If we go over to the testing data, we use the coefficients from the linear regression model, which you see here on this screen, and we use it to calculate the PE for the 20% of the dataset given for the testing methods. After the calculation, we see that the MSE value on the test data show an MSE of which equals to 20.74, which is in line with the value of the training data and in line with the expectations, which was 20.78 of the previous data. That was it. Thank you very much.